In the previous video, we went over electric dipoles, and I said that the maximum potential energy possible is this situation, because that the positive charge wants to rotate here, the negative charge wants to rotate here. The potential energy here is maximum, but also note that the torque is 0. Torque is equal to P sine theta. Theta here is equal to 180 degrees. Therefore, sine of 180 degrees is 0 and torque is 0, even though the potential energy is in a max value. However, at this point right here, where the negative charge is here, positive charge is here, potential energy is at a minimum, or a value of 0, because the dipole is not going to rotate through here, because the negative charge wants to be over here, the positive charge wants to be over here. And now we're going to go over plates of uniform charge. So imagine we have a plate that's very, very large, very, very wide, very, very long, and it has positive charges along it. These are positive charges. And we know that the electric field lines leave the positive plate and point away from it. But how do we know this? We went over earlier that we have a positive point charge. The electric field lines point away from it. But before I can go over the formula we're about to state, I need to give you an assumption for this formula. We assume that it is a huge plane or plate, and the charge that we're applying this formula to is very close. So if we assume all these things, then we can apply this formula right here. E, the electric field, equals omega over 2 sigma naught. Now this looks like Greek, and it is. So omega is the charge per meter cubed of the plate. And we know that charge per meter cubed of the plate is going to be coulombs per meter squared. Let me take that back. Meters squared. Okay, so we have this formula right here. But we're going to give you another formula also. But I'm going to have to explain another concept. So if we have a negative charge, it's the opposite of the positive point charge. And the charges point in. But this makes sense, because I told you earlier that the arrows indicate the direction that a positive point charge is going to move if you put it in that field. Put a positive charge here, it moves towards the negative charge. Opposites attract, likes repel. So, in this new situation, we're going to have two large planes. Same assumption applies as before. Very large, very close. One is positive, one is negative. And we know that negative, electric field points towards it, positive points away. So the field lines look like this. And notice I drew no field lines here and no field lines here, because there are no field lines, because the positive and the negative cancel what's out here. At first I was confused by this because I assumed that the positive charge is closer over here than the negative charge, But because of the assumption, we assume that these two charges cancel each other out for these two areas, right here and right here. So there is no electric field here and here. So we used this equation before, but now we have two plates. So we add this multiplied by 2, and we get omega over sigma naught. Sigma naught we know to be 8.85 times 10 to the negative 12 coulombs squared newtons per meter squared.